Welcome to this video tutorial. This is your teacher Karen, and for today we will be discussing enthalpy and entropy. So tune in and let's get this started.
The application of thermodynamic principles begin by defining a system that is in some sense distinct from its surroundings. For example, the planet Earth, a neutron star, a black hole, or even the entire universe. In general, systems are free to exchange heat and work and other forms of energy with their surroundings. A system's condition at any given time is called thermodynamic state. To further understand our topic, we will be focusing on the science of thermochemistry. Thermodynamics is governed by three fundamental laws. The first law, which states that energy can never be created or destroyed. The second law, which states that the total entropy of the universe must increase in every spontaneous process. And the third, the entropy of a pure perfectly crystalline compound at temperature 0 Kelvin is 0. Thanks to a Russian chemist named Hermann Henry Hess for his contribution in thermochemistry. One of the principles he developed is the Hess's law, which is of immense practical importance and is used to this day to determine heat of a reaction when their direct measurements are difficult or impossible. Okay, let's try with our first problem. So calculate the enthalpy of combustion for 1 mole of liquid ethanol using the enthalpy of formation values listed in the table below. So this is our equation. Then all the values for the enthalpy of each compound are listed already on the table. If you're wondering where we got these values, you can actually find this at the back of any chemistry book, or you can search this. These are already given. Now we have to take note that whatever answer we got from the enthalpy change of reaction, it will be equal to the change in enthalpy of combustion, because we are looking for the enthalpy of combustion. Now, the formula that we will be using is the enthalpy change of reaction is equal to the sum of number of moles multiplied to the enthalpy change of formation of product minus the sum of number of moles of enthalpy change of formation of our reactant. Now, all we need to do now is just to plug in all the values that are listed on the table to the equation using the formula given. Now looking at the table, you can see any value that were placed on the table for the oxygen, because oxygen has zero value because its enthalpy formation or its elemental state will always be zero because it takes no energy to form a naturally occurring compound. So we place 0 as value for oxygen. So our answer for the enthalpy change of reaction is negative 365 kilojoules. And the same value will be our answer for the enthalpy change of combustion. Now let's try another one. So what is the enthalpy change for the reaction shown below using the enthalpies of formation listed in the table? So this is our equation, and all the values of enthalpies are found here on the table. Try to observe the values in the table. The only value that is non-zero here is the ferric oxide. The enthalpy of formation of both iron and oxygen are 0 because both of them are in their elemental state. So same formula will be used in solving this second problem. So the enthalpy change of reaction is equal to the sum of number of moles multiplied to the change in enthalpy of formation of product minus the sum of number of moles multiplied to the enthalpy change of formation of our reactant. So all we have to do is to plug in the values found on the table. So this one, it's easier to solve because both iron and oxygen have 0 enthalpies or change in enthalpies. So our answer is negative 1652 kilojoules. So both enthalpy and entropy changes are important in determining whether a reaction will occur or not. A relationship between these two factors can be expressed by a new thermodynamic term known as Gibbs free energy. It was named after the American physicist Josiah Willard Gibbs. Now let's try to solve some of the following problems. Now we have to calculate the delta G at 290 Kelvin for the following reaction. So we will no longer solve for the delta H and the delta S because we have already given their value. So as you notice, there's a difference in their unit, so we cannot go through with the process of solving unless we convert the unit of delta S. So we divide it to 1000 so that we will get the value of negative 0.15 kilojoules. So they now have the same unit with the delta H. So the formula that we will be using is delta G equal to delta H minus temperature multiplied to delta S. So all we need to do is to plug in the values that were already given. And we will get delta G equal to negative 77 kilojoule. Now let's try another problem. Calculate the delta G at 350 Kelvin using the values of entropy and enthalpy given below. So same as with the problem or the first problem, the delta H and the delta S were already given. Now we also need to convert the delta S for it to have the same unit with the delta H. Now in some instances, if you encounter some problem wherein the delta H and the delta S are not given, you need to solve them using the same process that we did when we were solving for the delta H and the delta S. Now given the same formula, plug in the given and we get the answer of negative 10 kilojoule. And for the last problem, so calculate the delta G using the given below. So we are given with the temperature, we have the delta S and the delta H. Make sure that your temperature unit is always Kelvin. In terms you are given with a problem where the unit for temperature is in Celsius, you need to convert it to Kelvin. Same formula again will be used. And then plug in all the given. And we will get 61.44 kilojoules. Now try to observe the table. When we say spontaneous, it means that a reaction that occurs in a given set of conditions without intervention. A spontaneous reaction proceeds to completion without any outside help. Now, according to the second law of thermodynamics, a reaction is spontaneous if the overall entropy or disorder increases.